So welcome back to the CENTRA seminar, everybody. It's been a long time since I introduced that, so it's fun to be back again. Today, it is my great pleasure to introduce a long-time friend and collaborator, Anton Khirnov. Anton got his PhD in Prague, and with no hype, I can honestly say that the work of his PhD is basically the most important progress in this problem, for the problem that he's going to talk about, for pretty much 25 or 30 years. So this is really an important thing, and what he did in the PhD is genuinely like important work. And so over to him to tell a story.
Thank you. Thank you for introducing me. Thank you for inviting me here. It's awesome to be back in Lisbon again. I have to mention my supervisor, Tomáš Vedlinka, who is actually responsible for most of the physics. I am the software guy, but mainly. So what this talk is a bit of a trap. I will not actually talk that much about critical collapse because everybody knows what it is. David has talked about it a million times, I'm sure. I will very briefly mention what we did, but I will mainly talk about the software aspects of my work, which is architecture, efficiency, how to write it, how to make it fast, because this is like my specialty, my expertise. I also have to mention that I struggle to call myself a physicist. My main job is developing this thing, which some of you might have heard of. It's a collection of libraries for processing multimedia. If you do any video, audio, decoding, encoding, processing anywhere, you probably use this. And people working on multimedia are obsessed with performance, with making fast code, with writing code in assembly. So this kind of affected me. I have been working on this for a long time, and I think what I can tell you, what is interesting, is what kind of an insight can you get with a multimedia world view onto physics software development? What can you learn from that? So that will be like my main messages. So to start with, critical collapse keyword was discovered by Choptuik in '93. He did numerical simulations of a scalar field and spherical symmetry. He discovered that if you take one parameter configurations of a scalar field and make it weak, it will disperse. If you make it strong by taking large values of this one parameter, it will collapse into a black hole. And between these two regimes, you have what is now called the critical point, which is the point where the data is just strong enough to make a black hole. And close to this critical point, for evolutions of initial data which are close to this critical point, you get what is now called critical phenomena. It's called critical phenomena because it's reminiscent of critical phase transitions known from statistical physics. For example, power law scaling of various things like black hole masses of the black holes you create by this collapse. They scale like some power of the distance from the critical point. You get discrete self-similarity, which means that pieces of space-time repeat exactly on smaller and smaller scales. These individual repetitions are called echoes. You get universality, which means that the profiles of various quantities do not depend on the exact initial data family you take, but they are the same for anyone. And it's conjectured that exactly critical data will produce a naked singularity, which is interesting to cosmic censorship people, and it's one of the motivations for studying this. This was spherical symmetry, scalar field. People were also interested in studying critical collapse for gravitational waves, because then you're not influenced by the matter model, and you can study just the properties of gravity. Of course, for that, you cannot do in spherical symmetry because there are no spherical symmetric gravitational waves. You need at least axial. It's much harder because you have one more dimension, which needs more computer memory, computer resources, and there are more possible ways your data can behave, more possible modes of behavior. So that's another reason why it's much more complicated. Despite that, very shortly after Choptuk, not even a year after his first paper, Abrahams and Evans reported critical behavior with axially symmetric gravitational waves. They used what is now called Tucholsky wave as initial data, and they found very similar universality, echoing, scaling as Choptuk did for scalar fields. But nobody has been able to reproduce their results since then, and we tried and we could not do it. Reportedly, some other groups also. There were other attempts since then. Most of these other attempts use Brill waves, which are easier to construct. In 2011, Sorkin reports again success in finding critical behavior, but unfortunately, again, his results cannot be reproduced. David got closer than anybody else in 2017, way closer than Abrahams and Evans, and could not see critical behavior like universality and scaling like Choptuk's. So it's a lot more complicated. But me and my supervisor, we could actually find not exactly Choptuk's behavior, but something reminiscent of it. What we managed to find was echoing. So what you see here is a curvature scalar, which we call zeta, as a function of proper time on a world line through a peak of zeta. It's rescaled so that the minimum is -1. And what you see here is the data from 5 different peaks. And you see that the after rescaling with 1 parameter, the profiles look exactly the same. So this is a form of echoing, but it's only visible near peaks of this scalar, and it's not the entire spacetime which is self-similar. So we do not find evidence of generic self-similarity like in the spherical symmetric case. We find universality. What you see here is the same profile or like the same quantity for 4 different families of initial data, and again you see they are the same after a rescaling with 1 parameter. So that was the main result of my thesis. What did we use to obtain this? Our code is based on the Einstein toolkit. I will promote it later. We use the SSM formulation of the. We use zero shift. A big part of it was developing our own slicing condition, which we call quasi-maximal. It's an approximation of maximal slicing, which can be, which is more efficient. It doesn't require so much computer resources, and approximates maximal slicing somehow, which avoids coordinate singularities, because these are a big problem in this. David is also dealing with them in a different way. We use analytical cartoon method to handle axial symmetry. We use method of lines, we do it with the 4th order, finite differences in space, all very well-known, robust methods. We use fixed mesh refinement. It's not adaptive, the boxes are prescribed by hand. And with this setup, we managed to obtain these results. The main parts of it was really the slicing and optimizing the code, make it run fast though, so that even on our very limited hardware, we could run many simulations. And this will be the part I will talk about in detail. So the architecture of our code is, as I said, the Einstein toolkit, which is a bundle of the Cactus computational framework and some modules of Cactus, which they call thorns, to do numerical relativity. Cactus is an environment that in which you run your code. You write these modules for Cactus, and there is a special module which provides grids, mesh refinement on these grids, time evolution, and these thorns, they cooperate on the grids to evolve the data and construct the time evolution process. The code I wrote for Cactus, basically 2 main parts. Construct initial data, Brill waves, and the other family called time asymmetric waves. They are kind of like Abrahams and Evans waves, Tucholsky waves they used in '93, but not the same, which is one of the reasons we could not use that data. So each of these requires solving elliptic PDEs. basically the Einstein constraints. In the case of real waves, it's a linear scalar equation. For time asymmetric waves, it's 3 coupled nonlinear PDEs, which is why nobody does this. But we did that. I wrote them as a standalone libraries in C with some glue that integrates them into Cactus. And then the other important part is the slicing solver, which is a multi-grid elliptic solver for solving the quasi-maximal slicing equation. It's done during evolution, so it needs to be fast. So that was one of its main requirements. So it has some assembly code for it to make it really run faster. I'll talk more about this later. And there is a lot of non-trivial glue code due to interaction of an elliptic slicing condition with mesh refinement, which is quite non-trivial. And I think it's one of the reasons why people don't do maximal slicing much, because it doesn't, integrating it with mesh refinement is non-trivial. Other bits of software I wrote are some Python packages to process simulation data, like parent horizon finders, event horizon finders, constructing coordinates so we can compare data with, for example, with David or other groups, because they use different coordinates, so we need to construct them by one piece. Everything I do is open source. You can download it and run it yourself if you want. One important point is that, as you might see, Cactus is a framework for numerical code, but most of my code is actually alone. It's outside of Cactus. And this is because I find it, the framework approach, to be efficient. But what is a framework? What is a library? Maybe it's not clear. A framework is an environment for your code. It provides the arena into which you integrate your code. It typically provides some functionality that is useful for you. But really, the main point is that you put your code into the framework and it's in control. With the library, you are in control and you ask the library to do things for you. That is and you integrate the library into your code. That is the fundamental difference. Both approaches have their own advantages and disadvantages. The framework, which is used in physics, I think, a lot more. Most codes performing similar tasks are built using this approach. The framework does a lot of work for you. So if you're starting from zero, it's a lot faster to get to something that runs. Typically it implements a lot of things you might need, like mesh refinement, interpolation, integration, and so on. But there are many problems that I think are very important and not appreciated enough in the physics community, which is your code is locked into a framework. Once you choose one, it's very hard to get out of it. And if you find that the framework is limiting for you, which is a very common case, it's not pathological, it happens naturally to almost everybody, it's very hard to get it out. The framework is in control of how your code is executed, which means that if the design decision of the authors do not exactly align with your use case, if they did not foresee the thing you want to do, you will have a very bad time. For example, in our field, like web development, they used to use frameworks extensively and then found out that this has major disadvantages and people are switching away from that. And also typically frameworks are, by design, a giant pool of global state thing. I will talk more about what global state is, but let me just say for now that this is bad. But I will expand on this in a few more slides.
Can you give an example maybe of where you've seen, like in your, like an example from your own where you were like locked in?
Thank you for reminding me. Yeah, when I do my slicing is elliptical. Cactus is designed to be an evolution framework. So it assumes a lot of things about, basically it assumes you're solving hyperbolic equations. And if you want to integrate an elliptic condition into that, it gets in the way. And fighting Cactus was a lot of trouble for me. I spent massive amounts of time just fighting the framework because it was not designed to do what I wanted to do.
That wasn't like, we didn't set that up.
With a legitimate question.
Yeah, thank you. I wanted to say, but I forgot. So really, thank you. What about the library approach, which I'm kind of advocating? Yeah.
Just looking at the number of plus and minus points here makes it clear.
Yes, I'm somewhat biased because, but I like both approaches have their positive and negative aspects. But I think the framework approach is way more used in physics, and therefore it doesn't need that much advocacy. The advantages for the library approach: first, it promotes hierarchical structuring of your code. Because you split your code into libraries. A library is a standalone or separate package which does not depend, which only depends on what it needs to depend, and not on the entire framework. And you can easily tell what it depends on, and which makes it easier to understand what the relationship between different bits of your code is. It discourages global state. You can have global state with badly designed libraries, but it feels dirty writing it, so it discourages. It allows you to reuse your code more easily, which I think is not done enough in physics and not appreciated enough in physics. That a major property of computer programming and code you write for computers is that you can reuse it. I don't think it's done enough. And if one of your libraries which you were using or which you wrote is bad, and you decide you conclude that it's deficient and not good enough for a use case, you can replace it way more easily than you can replace a framework, because in a framework everything is entangled together. Of course, the disadvantages of this are that a lot more effort is needed to get from zero to something. You need to have a way better idea of what it is you're doing. So if you're completely clueless and just starting somewhere, then this will be hard. And you need to design library interfaces more carefully when you're doing it, because with a bad design, you again run into trouble, which will be a lot of work to fix later. So there are disadvantages, but there are also very important advantages, in my opinion. So my moral judgment, which I present to you for your consideration, is this: physics is using way too many frameworks, in my opinion, and it would be better for people if they used fewer of them. So I'm not saying they should be abandoned completely, because it's probably not practical, but people should look at the library paradigm more and give it more consideration. Please consider this message. Global state. I mentioned global state. What is a global state? It's a very evil thing. In general, a state is any data in your program which is mutable, which is not constant, and during the runtime it can change. For example, if you're using C or a normal imperative language, it's variable or an array or something like that. If you're being functional, it can be something weird, but then you know. If you read a textbook on programming, the first thing it tells you, do not use global variables, and then everybody goes and does it anyway, because people do not appreciate that global variables make your code unmaintainable. So, one of the disadvantages of frameworks is that they promote global state. They sort of guide you into using it. And one of the advantages of libraries is that they push you away from it. And I think this is not appreciated enough. I see tons of code in physics which uses global variables because you can write code with global variables much faster. It's much easier to get it to run, but in 2 months you forget how it works, and then reverse engineering how it works is impossible once you have enough global variables, because the complexity grows as the number of possible interactions, and when everything can interact with anything, it's impossible to make.
Can you give an example of that in the wild?
Of course. In Cactus, for example, there is one evolution grid, exactly one. This is a giant global variable, basically, and all the numerical thorns, they do things to variables on these grids. And it is very non-obvious, like in what order are things done? Who is responsible for what? Who owns something? It has to be reverse engineered from the code. Different bits make different assumptions, which are kind of almost the same, but not exactly the same. And figure out exactly what happens when something goes wrong is incredibly hard. And when you need to change something or take something into, separate something into a different library, for example, you cannot do it because everything depends on this giant bit of global state.
And sorry, building on that, what would the basic construction be to improve that? Like
The construct used for that is encapsulating the code or your things into objects, and then when code needs to do some work on some specific object, you pass it that object as a parameter. That is the canonical approach. It doesn't assume that there is a global variable, but it is passed to it as a parameter.
Okay.
And this ties into what I perceive as two different ideas of code development, which I call software as a product and software as a process. This is a naming I invented, but it seems appropriate to me. And I think that the product approach is more prevalent in physics, and the process is more prevalent in multimedia, where I'm from, or more generally in software development industry. The first one is software is a finished product. I develop it, I finish it, I test it, it does what I want. And the value of the thing I created is in what it can do for me today. The other approach is software is an ongoing project. It's not time limited. I develop it, and it continues to be used to me for years. And the bigger part of my software is the bigger part of the value of my software is in the future, in what I can extend it into, how can I reuse it, where can I take bits from it and copy somewhere else so I can reuse them. Of course, there is value in what it can do for me now, but it's smaller than the future value. And with the second approach, you're incentivized to make code future-proof, to make it extensible, to make it maintainable and readable, and against, for example, using global variables because they make your code unreadable. With the first approach, you're incentivized to use global state because it makes writing the code faster. You don't need to think much, you can just write it. But it goes against future improvements to the code because then you cannot understand it in 6 months, or your student cannot understand it in 2 years. It's impossible. With the second approach, it incentivizes you to think about the future work on the code. And I see way more of this in physics. I know there are incentives for it. You have to finish your PhD, you have to write papers, you have to get things done, and things which are valued is not typically not code you write. But having more of this approach, I think, will help you if you intend to do a lot of programming during your physics career. This will help you eventually. Also, it's not just about some single bit of software. It's also a lot about how you learn to write software. Once you internalize that you have to get software running and working quickly, you're stuck with that. It's very hard to unlearn. So again, what I would like to message here is that more appreciation for the future-proof development would be good. Let me move on to the second part, which is how to write efficient code, because we had very few.
No, so just,
Where should I start? Here.
whatever you want.
We didn't have many fast computers or any clusters or anything like that, so we had to make our code fast. There used to be a myth. There still is a myth. Computer power is growing exponentially, and therefore I don't need to optimize my code. It's a lie. It's wrong. It has not been true for about 10 years. Single-threaded performance of computers is not growing anymore, and there is no real space for it to grow, because all the low-hanging fruit has been obtained, and unless there are major revolutions in the way we build processors, this will not change significantly in the future. So what you do see growing in the last 10 years is the number of cores. So you need to make, for example, you need to make your algorithm parallel, or not, and you really need to start thinking about making your code efficient, because it will not just be magically solved for you in the future. So how do you make your things faster? The most important thing is parallelization, because you typically have many cores and you need to make your things use them efficient. So typically you have a cluster with multiple machines in it. You use massive passing like MPI to make use of that. In a single machine, you often have multiple processors. It depends on what is the most efficient. It could be MPI, it could be multi-threading. It really depends on the problem. Typically, in a single physical processor, you have multiple cores today. So you use shared memory, multi-threading, or OpenMP to parallelize on a single processor. But what is less known in physics, and I'm surprised that many people don't know about this, a single core in a modern CPU is parallel, and you can vectorize you can use that parallelization or built-in parallelism with what is called SIMD or vectorization. Compiled machine code looks basically like this. Here on the left is really what your CPU eats, and this is there's roughly a one-to-one correspondence between what's on the right-hand side. This is assembly language. This is what your computer executes. So typically you have an instruction which does exactly one floating point computation. So this is an add, this is a multiply, this is moving things from memory, and so on. But a common pattern in say numerical physics or other, in multimedia too, in many tasks, is that you have a large array and you need to do the same operation on many elements of this array. So modern processors have this capability, which is called SIMD, single instruction multiple data, where you execute the same operation on multiple numbers at once with a single instructions, and in theory you get a speed up by the size of your vector. So you have a vector like this. For example, this is 4 numbers in a vector, and you do the same operation on all of them. Here is a pair of vectors. For example, it could be a plus or a multiply, and in theory it's 4 times faster. It can be more, it can be less because of very complicated reasons I will not go into, but on average it should be 4 roughly. And almost all processors you will encounter have this capability, and if you don't use it, you're using 1/4 of what your CPU can do. But actually generating SIMD code is still non-trivial. So there are several ways to access it. You can write assembly by hand. I will argue that this is what you should consider, at least, if not do. You should consider it. You can use what is called compiler intrinsics. You can rely on your compiler to vectorize your code for you. You can call an external library which a nice person already vectorized for you, or you can use higher level tools. I will not talk about them. There are some libraries to generate SIMD from by magic. I have no experience with them. They do exist. You can try to look them up, but I will not talk about them. Vectorized libraries, like if your problem is a matrix multiplication or something expressed with plus or LEPA, you can use OpenBLAT or MKL or some other optimized implementation which does use SIMD, and your code will be fast. So that is great. Very little work for you, but it works only if your algorithm is efficiently expressible as BLAS operations, which is not always. Compiler vectorization. You let the compiler do your work for you. No extra work. You just set some compiler flags and magic happens. Unfortunately, it is very unreliable. Still, you might get some speed up, you might get no speed up, you might get broken code. It depends on which compiler you use, which flags you give it, which version it is, the phase of the moon, and so on. And the result is non-portable. You cannot really copy it between computers. So there is no free lunch, fortunately. In relation with this, I have to discuss many physicists that I have encountered believe in this. The compiler is super smart and it will generate optimal code, and you don't need to do anything to help it. It's not true. It's still not true, and you should not believe. Why do people believe this? In ancient times, compilers were very primitive. People used all kinds of really ugly, hacky tricks to make them generate fast code. And this code was buggy, non-portable, unreadable, unmaintainable. But eventually compilers improved, like after the year 2000 roughly, and this stopped being necessary. So compiler authors were trying to convince people to stop uglifying their code for no reason. So they invented this make, and they were too successful. Now people tend to think the compiler is amazing and will do everything for me. So it's not that compiler is completely dumb anymore, but it's also not super smart. So why is it not super smart? So I'm absolutely not denigrating compiler writers. They are super smart people, super competent people, way smarter than me. But the priority for a compiler is not fast code. The top priority is correct code. So it needs to conform to standards. It needs to conform to some historical accidents which were not foreseen, but it needs to keep compatibility still for things which were designed 30 years ago. It needs to handle, for example, for floating point numbers, you have things like infinities, nulls, and denormals, and all this stuff, and it needs to be done exactly according to specification. And floating point math is not associative. Probably many of you know that, but maybe some don't. And so it cannot do many kinds of optimizations for you because the standard doesn't allow it. It also has very limited information. It knows less about your program than you do. The compilation also has to finish in finite time. So which severely limits what a compiler can do. So you shouldn't try to trick the compiler. You should try to help it to generate good code. And if you don't, there are good chances that the code it generates will be very suboptimal, to put it very mildly. But how do you help it? To do that efficiently, you need to know what a compiler produces, which is machine code, which I showed you earlier. So to really do this efficiently, it is a good idea to know at least some assembly language, which is one reason why I'm saying that it's a good idea to learn it. Even if you don't write it, it's good to know what a compiler does with your C or Python or whatever, Julia, whatever language you use. You should know what actually gets executed on the hardware. And it's not that horrible. You can learn it in reasonable amount of time. So enough of this information, back to generating SIMD. The one other way of generating SIMD I mentioned is what is called compiler intrinsics. It looks like special functions, special data types that you use in your language, like C, for example. And the compiler handles things like register management, stack management, whatever these things are. Typically, it's within 10% of handwritten assembly. People often consider that intrinsics are easier to write. I do not agree with this, actually, and I will show you why in a second. And the final option, which I will discuss, is handwritten assembly code, which, again, it's typically fastest if you know at least a bit of what you're doing. People consider it hard to write. I disagree. I think it has a reputation which is not entirely deserved, because high school students wrote assembly code for FFmpeg that was then used in production, and it was faster than C code. It does require you to know what the target CPU and architecture is, but as I said before, if you want to write fast code, you need to know that anyway. So let me finish with an example. So for constructing real waves initial data, which were we solved the constraint equations with a spectral solver. So we have a matrix of spectral coefficients, and now we need to evaluate it at some point in spacetime. To do that, we need to do this kind of a sum with the values of the basis functions at some point, and it's this kind of a loop. In C, it looks like this. You can write it in 10 minutes with one finger. It's quite straightforward and obvious. You could write the same thing in assembly. You see that it looks longer, right? It's longer. It's about 4 times longer for a good reason, because the code is unknown. I repeat operations 4 times for technical reasons. That's the main reason why it's so much longer. Otherwise, I mean, it's not so horrible. It's not 10 pages. But if you write this in intrinsics, it looks like this. People often feel more comfortable with this because, oh, hey, double, semicolon, 4 in something. It looks like code I know. So they think, for that reason, many people think that this is easier. But my argument is that there's actually a lot more visual noise here. Like this is less readable than this, in my opinion. And the difference is not that substantial. You still need to know what the instructions are. So you might as well, instead of using intrinsics, might as well write assembly. So this is my message. Please consider it. If you compare the results, so scalar code. So this was the C code which I showed you initially. If you pass O0 to compiler, it will generate something which you should never ever use. This is horrible. If you use O3 to a common compiler, it will generate something like this. 3 different versions of compiler optimizations. You see that ICC conforms to the myth that ICC is fastest, which is not always true, but it's true here. But generally, GCC is worse. Okay, it's way better than unvectorized code. OpenBlast is really good here. MKL is really sucks for some reason. I don't know why. If you write intrinsics, which I showed you here, it's this. They are almost the best, but handwritten assembly beats it by 10%, which is typically the rule of thumb that handwritten assembly is 10% faster. Nobody cares about that 10% in physics. In multimedia, people do, but there are other reasons why it has to be like that. It's more fun. But what I should also, it is really, it's like a puzzle. It's very zen. One thing I should emphasize, this is super simple code. Like this is the simplest non-trivial example you can come up with. Typically, when people demonstrate compiler auto-vectorization, they use a single loop because then their compilers work. So this is a double loop and they stop working. They don't stop working. They do not that badly. GCP does badly. But yeah, it's still not as good as it could. If you go to something more complicated, there is a force for my slicing solver, which needs to be very fast because it runs during evolution. We need to evaluate the residual of an elliptic equation. It's something like this with finite differencing and basically second order, the general form of a second order residual. Scalar and optimized, again, horrible, never do this. Scalar optimized with O3, meh. Compiler vectorization really sucks. It does really badly because this is just too complicated for compilers. They cannot handle finite differencing. Handwritten assembly beats it by a factor of 4. So I didn't write intrinsics here because it would be too much work just for this case. I think they would be somewhat comparable with handwritten assembly. Just my point is, it's not that much less work to write intrinsics, or maybe less work at all. But yeah, if you're into code that looks like C, you can write intrinsics and get somewhere. But if your code is this, which it likely is, consider how much performance you were leaving on the table. Okay, so that's almost everything. I think people in physics should consider future-proofing their code, more libraries, less frameworks, more code reuse, more upfront design. Compilers really need your help to generate efficient code. Otherwise, you will get something that runs but is really suboptimal. If you don't vectorize your code, it will be horrible. I see like there's a lot of focus in physics on scaling. People love linear scaling graphs, but they never ever measure how much of your computer's theoretical performance you're actually utilizing. So it could be that all this amazing scaling comes with the fact that you're using your processors very inefficient. So if you have limited CPU time like me, then you might consider expending some effort on making your code faster. Thank you.
All right, time for questions. Yes,
I
Mr.
have two. One, the first one is very dumb. I guess like this time you need something like a cartoon method for Axisymmetric.
Yes,
I
it's
don't know why you have
how is it possible. Uh, I stole it from David. So in axial symmetry, right, you can replace derivatives in the y direction or the phi direction by analytically known prescriptions, right? Because that's what axisymmetry is. And if you do that before when writing your code, when generating it, then the code that actually gets executed, it only has like x and z derivatives, no y derivatives. And this is contrasted with the old cartoon approach, which exists in Cactus, where it actually generates a thin slice of points in the y direction, which it fills with interpolation, and then it actually it leaves the y derivatives to be performed in the code, but only on this thin slice, and this is horribly inefficient. So that's the difference between the old cartoon method and the analytical cartoon method. The analytical means that you replace the derivatives explicitly.
Has your new version now been absorbed by the Einstein toolkit framework?
No,
So it's probably-
I have not actually, like my Einstein toolkit is from 2013, and after that I've been too afraid to upgrade it. So I have had no interaction with newer versions. Because who knows what it might bring. Yeah.
So we work with maybe a framework, I guess is the word.
You can use the word. I won't kill you.
No, but it's got vectorization with, I think, the piece approach. So, but to my understanding, tell me if I'm wrong, because I'm not an expert in this. Like the way it vectorizes depends on the processor, and so like these very complicated names change according to that.
It changes depending on the architecture. So if you're using, if your code runs on servers, it will typically be x86, so like Intel/AMD style architecture. And then it is, all the CPUs are backwards compatible, but as time goes on, they release newer versions with wider vectors. So the original vectors were 64 bits, back in Pentium days. Then there were 128 bits, so two doubles, then AVX, which was 4 doubles, and now we have AVX 512, which is 8 doubles. But this is backwards compatible, so on the newer processors you can still use the older vector instructions. They just won't be the most efficient thing you can use on that.
Okay, yeah. So, but my question was, so how much do that extend to the way you write code?
Sorry, I don't understand the question.
Yeah, like the lower level code, like
How, what extends to it?
no, I mean like how does that depend on the way the compiler vectorize, or which kind of architecture we have?
Yes, I'm going somewhere here. So
Yeah.
So this is what your CPU executes, and the format of the left-hand side depends on the architecture. So x86, for example, uses one encoding or one instruction set. If you had an ARM like your phone, some people say that in the future we will have ARM everywhere. It has not happened yet, but when it will, you will have different, or if it will, you will have different instructions and also different optimal way to use that. That is one big disadvantage of assembly, is that it depends on the architecture, but then it doesn't change too much. Today, everything is Intel x86, essentially. And then the instruction set is fixed, it's backwards compatible. They can extend it in the future, but features typically do not go away. And the correct approach, which it also fits into my discussion on architecture, the correct approach, typically a very small bit of your code is performance critical. You identify that bit, or you know which one it is because it's obvious, but you should measure anyway to identify which one it is. Then you isolate that bit into a function then you always call that function through a function pointer in C. And then what you do is you write multiple implementations of that function. So like a standard C version, an assembly version for this, that architecture. That's what we do in multimedia. And we have like however many versions of that function we want. And at runtime, you check on what processor you are running on. You set the function pointer accordingly, and then you just call it. And the code which calls it doesn't care what happens inside. So it's completely agnostic. Yes.
I guess can you comment on whether, or I guess whether this is applicable or what changes if you program or if you write for GPUs?
GPUs. Essentially, for GPUs, you have to write your code entirely around them. So for that reason, I am mostly avoiding GPUs because it's all very opaque and proprietary, and essentially you're at the mercy of NVIDIA, and your code will only ever run on NVIDIA. And you have to design your code around everything being on the GPU, and they have very different properties in terms of like memory latencies and stuff like that. So
Is that practical in the multimedia world? Because you have to run on a lot of GPUs, right?
actually, no. What people think of when saying my video decoding runs on a GPU, it's not actually executed on the processing units. They have a special chip specifically for decoding video. So you just send your data to this chip and it gives you back decoded frames. You don't actually write like CUDA code for decoding video. We do have some CUDA code for filtering decoded video, and that is handled in a similar manner, like I just described. We have function pointers which execute some code, blah blah blah. But it's made more complicated by the fact that GPU memory is special. You cannot just access it. You have to interact with it through special APIs. It's a lot more complicated. And that's what I dislike about GPUs exactly, that everything has to be special about them. But also, there's a whole lot of PR around GPUs. There's a whole lot of people coming in with and comparing unoptimized, unvectorized C code with specially written GPU code and saying, hey, these GPUs are faster. And they are not really considering that they are not using their CPU properly. So I avoid GPUs when I can. They have very little memory, which is a big problem for some applications, not for all of them. But if you need a lot of memory, you typically won't get it on a GPU.
More questions?
How do you learn if your task is aligned with the framework, the assumptions of the framework? I expect you to be now an expert on scientific documentation. What are your tips to go through documentation to maybe avoid reverse engineering the code?
Typically, my initial assumption: a framework is a bad thing which will kill me eventually. Because in my experience, if you try to do something non-trivial, you will run into the limitations of the framework. And you always want to do something non-trivial in physics because the trivial things were already done before, right? So then almost always you run into the limitations, and then you can tell by that the framework doesn't align with you by the fact that writing things becomes very hard. I don't really have a better metric for it. Yes, you can read documentation when it exists, which is not always the case.
More questions? Maybe I can ask questions as well. First thing I wanted to ask you, so you were talking about the limited hardware resources that you were having, especially doing your PhD. Like what type of infrastructure did you optimize your code for mostly?
So what we have like a Czech national computing infrastructure, which students get free access to, but it's first come, first served. So we don't have like guaranteed 4 hours. We have, you submit your job, and when it gets when there's a free machine for it, it will run, like it gets into a queue. But I found a cluster of like these weird machines, which are Intel Xeon Phi, which was like this weird hybrid between a GPU and a CPU. It has a normal architecture. This code executes on it. Its general purpose performance is super slow. So in normal unvectorized code, it's as slow as these old netbooks because it uses the Atom architecture for those. But also this very tiny, low power, cheap, slow core is coupled to AVX512 vector processing unit, and there's 64 of them on the machine, these are boards on the board. So it has super amazing vector performance, but ultra horrible scalar performance. So if your code is vectorized, things run very fast. If your code is not vectorized, it runs very slow. And because nobody's code is vectorized, these machines were seen completely unused. So I was using them.
Then actually I wanted to ask something else. Because you were talking about how it is worth to actually spend the time, like when you want to optimize something, to actually either write the assembly code or at least see how you can improve it. But I mean, that also comes at an expense that you really need to spend the time doing that and like instruct yourself. Like I myself, I mean, I can do basic coding, but I don't know about these things. Like how much would it take me, for instance, to be able to get at the level where I can develop these things?
That is a good question. I cannot really answer how long will it take you, because I already know this thing, and it's really hard to compare. I think like getting a very basic idea of how assembly code runs is like a week of study. For me, it was, I read through an assembly textbook. There was literally a textbook aimed not at vectorization, but at general purpose assembly, which nobody writes. Like nobody writes the entire programs in assembly like people used to. But for vectorization, you don't need all features of your processor. You need to know the vector instructions and like basic looping instructions and like the basics. So you don't need to know it in detail. You just need a general outline. I think a week for like getting a general overview and something like it's hard to really gauge, because writing your first assembly function that actually works and does what you want is a long and painful process. But once you get that first one, then it becomes a lot easier.
Thanks.
I do understand and appreciate that it is an investment, but my claim is it's an investment that pays off if you expect to be doing a lot of programming during your career.
Maybe if there's no more questions, we can ask another one, which is related to this, which is okay. And knowing, I mean, in the like the current state of research, well, that's what you mentioned. Like we need to produce papers, we need to finish our PhDs, we need to get another postdoc. Like there's no limited time that can be spent on this. So do you think it's a better scenario where each person is thanks. Do you think it's a better organization in which each person is able, at least to some extent, to understand like from the low level to the high level, or to better have like people who work more with the physics bits or work more at the high level degree, and then have some experts which can do the coding better? What do you think works best, or what you?
I think the model where you have experts on physics and experts on programming is really good in theory, but experts on programming are very, very expensive. So if these are people who are doing it for money, and you are just hire them, then no physics department would be able to afford it. So they have to be physicists who love physics and want to do physics, otherwise they won't be doing it. Or people, physics department need to be getting a lot more money from the governments. Yeah.
Okay, thank you. Last chance for questions? All right, then there's then can speak again.
If you enjoyed the video, like and subscribe.